Hello. In the last videos, we discussed many problems of DSU. Let's discuss the next one. Here is the question, read it and give it a try. A string is called magical if it satisfies the building conditions. The length must be exactly n. It can contain only lowercase letters, and for each pair in the input, the substring must be a palindrome. Return the answer modulo 1 in n plus 7. And the conditions are n is up to 2000 and the m is up to 2if. So m is the number of pairs that we get, saying that L to R must be a palindrome. So return the answer. So let's take example. So n is equal to 5 and let's take a string of ABCDE. This is not characters. Let's just assume that these are some of the variables that need to be filled to make the query satisfied. So if the query is only 1 and it is 1 to 4, it means that A should be equal to D and B should be equal to C because it must be a palindrome. So for it to be a palindrome, A is equal to D and B is equal to C. So for a query L to R, we have to make sure that the characters at L and R are equal, L plus 1 and R minus 1 are equal, and so on, till we get a single value, whether that can be XX or whether we reach the smallest pair, that is X plus 1. So in this way, if we try to do for every query, the time complexity will be the number of queries into what is the maximum operations that we can do for query. It can be n by 2, because for example for 1 to n, we can go till 2n minus 1, 3n minus 2 and so on. Then we can try to, because we can reach midpoint n by 2 or n by 2 n by 2 plus 1 based on whether n is odd or even. So approximately the number of queries are n by 2. So what will be time complexity if we try to traverse every query and make every pair equal? It will be 1e5 into m is up to 2e5, so it will be approximately 2e8, which is not possible and we have to optimize this. So how can I do this? So for now, let's just now to think in terms of time complexity. Now let's try to solve. Now, because let's assume that m into n is up to 1e6 or 1e7. So let's try to solve how can you do this. So for 1 to 4, A and D are B and C are equal. So B and C and A and D should be equal. Whether A and B are equal or not, B must be equal to C and A must be equal to D. And if the next query is 4 to 5, then what is the case? So then we have to make D and D equal. So we have to make D and D equal well in the following query. So if are you able to observe something? So for every query, we are trying to make every value is equal. So only in the first query, we have made A equal to D and B equal to C. And coming to next query 4 to 5, A, D are already equal. Let's assume A is equal to D is equal to X. So A, D are already equal. And then we are trying to make E is equal to that value. So then we are adding X to this value. So if we try to clearly observe, it is simply assuming the property of DSU or giving the chances of DSU, like we are trying to make all values of a connected component equal. So for this, if we store all the equal values in DSU, for example in the first query 1 and 4, so 1 and 4 are equal. So we are trying to make a single ultimate value for the whole component. So we can store 1 and 4 in a single DSU component, and we can store 2, 3 in other component as well. And now coming to 4, 5, 4, 5 must be equal. So what is the ultimate parent of A? Here A is equal to D. So A is equal to 1, D is equal to 4. Let's assume the ultimate value is X. So the new ultimate value of E must also be equal to X from this operation, from this query. So obviously we are finding the ultimate parent of 4. It will be 1. So we are adding 5 also in this component. So in this way, for every query, if we try to make all operations and if we try to make DSU, then we can simply do the pre-processing. And now coming to, so for now we got how to do if product of m into n is up to 1e7 or up to 1e8. But now we have to reduce this also. So what are some optimizations that we can think to reduce the queries processing? So the simplest thing is sort by increasing L. After the optimizations, the main goal is to make sure that we are not making redundant operations. So coming to the first idea, sort by increasing L. So let's sort by increasing L and let's assume that these are the queries. So for 1, 2, we'll make 1, 2 in the single query, and for 1, 3, we have to make 1, 2, 3 in the same component. So this means that 1, 2, 3 are all the same component. And now coming to 1, 4, obviously we have to make 3 also to the 4 also to the same one, and we have to go to 2, 3 as well, because there is no information that 2, 3 are already connected. Because what if the first query is 1, 4? So obviously for every query, we cannot just add the last values. We have to go for inner values as well. So for 1, 4, we have to go to 2, 3 as well. And we have to check whether they are already connected or not. If connected, then don't do anything, then go for inside. And similarly all. So even after by sorting, we are not reducing any blend operations, because for 1, 2, we have to make 1, 2. For 1, 3, we have to check 1, 3, 2 as well. For 1, 4, we have to check 1, 4, 2, 3 and all. So obviously by sorting, we are not making anything beneficial. So it is best to think of this. And now coming to next one, sort by increasing R. So even now it is the same case, because for 1, 5, we have to check for 1, 5, 2, 4 and 3 whether they are in same component or not. Because we are not sure that 2 and 4 are already pre-processed earlier and they are already connected. So obviously this is also not good. So coming to 2, 5, again we have to check 2, 5. Again we have to check 3, 4 and so on. We are doing return operations every time, because we are not sure that a query is already processed and that information is already stored in the DSU. We are not sure that. So even now the optimization is waste. So think of more examples where we can try to optimize the processing. So let's check this one, right? So for example, 1827353645. So this is the first set of examples where we try to think what can we do. So for 18, so this is the first query. So we have to make sure 182736 all 5 all in a single connected component or not. So we have processed the first query. It seems that again we are wasting the operations, but just wait, let's complete this all queries and now let's try to come to take a decision. So we completed all these and now coming to the next one, 27. So even now 27 you have to make everything right, because we are not sure we have connected the inner queries or not. So even now we have to merge the every inner pair. So even for 3, 6 we have to make 3, 6, 4, 5. So even for 4, 5 we have to make 4, 5. So if you observe one thing, we can try to come in the reverse way, right? So for 4, 5 we can make 4, 5. And coming to 3, 6, so we have processed already 4, 5 here. So what if we store something that 4, 5 is already processed and all the information regarding this is stored in already in the DSU. So if there is some information like that, then we can just only try to make operation for 3, 6, because we are coming from reverse. The first one reverse, which will be in the reverse, is 4, 5. So for 4, 5 we will do the operation. We will store 4, 5 in a single DSU. And coming to 3, 6. So coming to 3, 6, there is no operation till now performed on 3 and 6. So now we will make 3, 6 a single connected component. And now if there is an information saying that yes, we already done the query for 4, 5 and we already merged 4, 5 in a single connected component. What if there is something like this? Then we can simply, it will take off an operation to process this, because we'll just connect 3, we'll merge 3 and 6 and there is no need to go inside, because we got that this is already pre-processed. And similarly coming to 27, so what if just we combine 2 and 7 in off one, and what if we have some information saying that 3 to 6 is already connected, 3 to 6 is already taken care of? That means we have already done the changes in DSU. So this is the main observation. So instead of doing the query for every query in operations, what if we try to do some off on operations for some queries after pre-processing? So similarly coming to 1 to 7. So if we try to do 3, 5 first, we'll merge 3, 5. And for 2, 6, we have to merge 3, 5 again. Because for 2 to 6, 3 is 1, 3, comma 5 is the inner one. And for 1 and 7, 2, 6 is the inner one. So if we try to observe one thing, the main thing is boiling down to a single value, right? Because for 1, 8 and 2, 7 and 3, 6 and 4, 5, the only value dependent is the middle value. Because anyway, we are going to come in the reverse value. We are coming the reverse value, decreasing order of L. So what if we store a value of a mid saying that the operation is already pre-processed? For example, we'll start with this one, right? So we will start with this one, simple one, and coming from the reverse one. So initially we are starting from 4, 5. So for 4, 5, what we need to store such that we need to say for 3, 6, 2, 7, 1, 8 that it is already pre-processed. So let's say we have 4.5 because this mid value. For this mid value, let's say we have already computed for 4, 5. Because for 4, 5 there is simple off on operation, we will merge 4 and 5. But now coming to 3, 6. So coming to 3, 6, we will check the midpoint. Is midpoint already there in the map? 3, 6. This midpoint is also 4.5. Midpoint is also 4.5. So is there a way to go inside? Obviously there is no, because it is just enough to store information of 3, 6 in the DSU. So we already got this one. And similarly for 2, 7, what is the midpoint of this one? It will be 4.5. So instead of processing everyone, we can try to make a map where the first value is midpoint and second value is the largest pair with the highest range. Because let's say for 4 and 5 we are storing 4.5, and what should be the right value in the map? For example, we are storing map in comma something. So for 4.5, what we should store? We should store the highest value with that midpoint, right? Because instead of processing 4, 5, 3, 6, 2, 7, if we only process 1, 8, then we can store all these informations also in one go. Instead of doing operation for 4, 5 or 3, 6 or 2, 7, if we do only operation for 1, 8, then for 1, 8 we are going to make 1, 8, 2, 7, 3, 6, 4, 5 in DSU. So instead of doing every operation bluntly, we can try to store map with a pair with highest range, so that if we try to cover that range, all the inner subqueries also will be resolved. So in this way, by simple observation, we can make sure that we will store map of int comma pair. So there may be some difficulties with respect to using double. So simply we can use pair of int comma int. If it is 4 comma 0, it means that it is an even midpoint. So for example, we have 3 to 5 and we have 3 to 6. So for 3 to 5, what is the midpoint? It is 4. So in the pair, we will store this as 4.5, 4 comma 0. And similarly for 3, 6, what is the midpoint? It is 4.5. So we will store this as 4 comma 1, so that there is no problem in storing doubles or float. So for 4, 0, we will store 3 comma 5 in the map. And let's say we got 2 comma 6 also in the further operation. And for 2 comma 6 is also the midpoint is 4. So we will check which is the higher range. So initially for 4 comma 0, 3.3 comma 5 in the map. So what are the number of operations? What are the number of count in 3 comma 5? It is simply 3, 3, 4, 5. But for 2 to 6, what are the number of numbers in the range? It will be 5. So obviously we will replace this with 2 comma 6. For 3 comma 5, we did not do any processing. We just stored the value in the map. So even for 2 to 6, we are not doing operation. We are just finding the number of numbers in the given range. And if it is already greater than what in the present map, then we are replacing that with the original pair. So in this way, after the map, we will have all the pairs and optimal values that we can get. Optimal pairs, which those traversals may be sufficient. So, but what is the proof that we have decreased the number of operations? So what can be the number of possible midpoints? For example, we have 1 trillion. What are the number of midpoints possible? It is only 2n, right? So can 2 be any midpoint of any pair? Yes, for 1 3 can 2 be a midpoint. Can 2.5 be a midpoint? Yes, for 1 4 it can be a midpoint. Can n plus 1 be a midpoint? No. It should be cannot be a midpoint. So because we have only till 1 and n, so how can any other value be average of those both? So obviously our values will be from only 1 till n. Can the midpoint be 1? Yes. It can be 1 for 1 and 1. For L comma R 1 and 1. So in this way, we can have value 1, 1.5, 2, 2.5, 3 and so on till n. So what are those numbers? It will be simply 2n. So instead of processing every query, we can store at most 2n values in the map. And for every value and for every midpoint, we will have the pair with highest range. So after this, then we can try to use a simple DSU, and then we can traverse everything. Because after this, what are the number of computations? It will be simply n into m. It will be 2n square, because we have reduced the number of queries to n. So it will be 2n into, let's assume that for every query we are making O of n operation, n by 2. So it will be 2n square. So the n is 183, right? So in this way, instead of going for every query, we can store in a map what is the highest range regarding that midpoint, and then we can find the answer. So we finally construct DSU and n square. We computed the map, and after traversing the map, we will traverse for every value, and we will merge all the inner operations, and similarly for all, because this can be up to 2n, and for every map value we can go till n. So the time complexity will be n square only, not greater than 1/8. So now how can you find the answer? So after DSQ we got number of connected components. So let's say 1, 2, 3 is one connected component and 4 to 5 other. So what will be answer? So for connected by 1 to 3, what is the restriction? The only restriction is that every value in this component should be equal. So it can be 1, or it can be A, or it can be B, or it can be till Z. So there can be 26 possibilities. So what is the answer for this? It will be simply 26 only, because we can assign A to all of the below, all of these, and we can assume B to any of all of these. So what is the number of what are the number of possibilities we have? It is simply 26, because for every A we can assign all 1 to 3A, for every B we can assign all 1 to 3B, and so on. So let's say we have other component also. So for 4, 5, even there is 26. So let's assume this is the whole new graph. And now what will be the answer? It will be 26 square, because we can make A to 1 to 3, A to 4, 5 as well. There is no restriction that two different components should have different values. The only restriction is that every connected component should have all same values. So these can be A, or these can be AB, or these can be AC, and so on. So for this possibility is 26, and for this also the possibility is 26. So simply the answer will be 26 square. So for n connected components, the answer will be 26 power n, because every connected component is independent of other. So for every connected component, we have 26 values, 26 possibilities. So for net n components, the answer will be 26 power n, which can be simply done by modular exponentiation, which we have discussed in one of the previous videos. So in this way, we can return the answer. If you have any doubts, comment below. See you in the next video.